Ghost hunters use many tools to detect signs of paranormal activity. One popular method is to use a flashlight to communicate with a ghost. The method has become known through the TV show Ghost Hunters, and it has been adopted by many ghost hunting groups. It works like this. The ghost hunter takes a flashlight that can be switched on and off by turning its head. Then he turns it to a position between on and off, creating a loose contact. After that, he puts the flashlight on the floor or on a table, where it usually goes off. Then he starts asking questions to make contact with some ghost. Like, is there anybody here? Or could you please turn on the flashlight? Eventually, the flashlight turns on, as if touched by a spirit. The ghost hunter might now ask the ghost to turn the light off, and eventually it goes out. The ghost hunter continues asking questions and, amazingly, the flashlight seems to confirm by switching on. This can go on for a while. Anyway, the ghost hunters think that they are communicating with ghosts through a blinking flashlight. Well, we are not going to discuss whether it makes sense to ask a spirit to operate a flashlight. This video is about how it works. Why does the flashlight go on and off again and again? I tried to get the flashlight for which the effect has been confirmed. When examining close-ups in some videos, I could identify the flashlight used as the Mini Maglite 2-cell AA Xenon. This is the version not having an LED but an incandescent light bulb with a power rating of 900 mW at a voltage of 3 volt. I bought one of these, and after fiddling with it for a while and switching it to a loose contact position, it did the trick. It went on and off again and again. It did that for hours, and I did not have to talk to any ghost for that. I did not even have to be present in the same building. To get an idea of how the trick might work, let's take a closer look at the flashlight's design. The hull of the Maglite is completely made of aluminum, and you can switch it on and off by turning the head. But unlike most other flashlights of this kind, it goes off when you tighten it by turning the head clockwise, and when you unscrew it, it goes on. By turning the head clockwise, the reflector of the flashlight presses on a switch cylinder that carries the light bulb. The switch cylinder again carries a side contact that touches the aluminum hull. When the reflector pushes the switch cylinder into the barrel of the flashlight, the electrical circuit is opened and the light goes off. Conversely, when the reflector releases pressure, then the spring in the tail cap pushes the switch cylinder through the batteries so that the side contact touches the aluminum hull again, so the light goes on. Now, some people think that the cause of the flashlight going on and off might be knocks or vibrations in the environment. It is true that the lamp can be switched on or off this way, but the trick also works when there are no shocks at all. There is also the theory that the metal of the hull is contracting and expanding under the heat of the light bulb, and that these movements cause electric contact to be made or broken. When measuring the temperature of the hull while the lamp is on, it becomes evident that the aluminum hull barely heats up. However, the interior parts of the flashlight heat up quite a bit. The measurement reveals that the reflector can easily heat up by 13 degrees Celsius. Now, the reflector is made of plastic. Plastic is a bad heat conductor, but it does expand under heat. By the help of a microscope camera, I tested how far the reflector expands and contracts. I just heated it up with a hairdryer and then took pictures of it during the cool-down process. It turns out that a temperature difference of 13 degrees Celsius results in a heat difference of roughly 0.01 millimeters or 10 micrometers. Let's see how an expansion of 10 micrometers translates into turns of the flashlight's head. The screw thread of the flashlight's head has roughly 8 gaps at a distance of 11 millimeters. This means that a full turn of the flashlight's head moves the switch by 1.375 millimeters. So a displacement of the switch by 0.01 millimeters is equivalent to a 2.6 degree turn of the head. Seeing how sensitive the flashlight is when being in a loose contact state, a turn of nearly 3 degrees seems more than enough to switch the flashlight on or off. But there are 2 more experiments that support the idea that the blinking of the flashlight is driven by thermal deformations of the reflector. The first experiment is actually the simple observation that the flashlight trick does not work when the flashlight is at room temperature. If the flashlight has been off for a longer time and you immediately switch it to the loose contact position and it goes off, it will not go on again. When trying the trick with a cold flashlight, you need to switch it on for at least 20 to 30 seconds before making loose contact. Otherwise, there will be no on-off cycle. This observation does not only indicate that the trick really depends on the heat of the lamp. We can now also identify the piece that needs to be heated up to start the cycle. If the trick works mainly because of the reflector heating up and cooling down, then it should be enough to heat up only the reflector to initiate the cycling. You can take a hairdryer to separately heat up the reflector before reconstructing the lamp. If the reflector's thermal deformation is not involved in the flashlight trick, then nothing should happen, just as nothing happens when the trick is started with a cold flashlight. But as it turns out, the heat up of the reflector is actually enough to initiate the cycling. Let's try to figure out what exactly is happening. When the light bulb goes on, then the reflector expands and presses the switch cylinder down until contact is broken. Conversely, when the light bulb goes off, then the reflector contracts and reduces pressure on the switch cylinder until contact is made. However, there is something missing in this picture. When the lamp switches on, then why does it stay on for such a long time? Conversely, why does the lamp stay off for such a long time, sometimes even for many minutes? Let's do some temperature measurements. Here the temperature of the front plate is measured. This is not the same as the temperature inside the lamp because the IR thermometer also captures reflections of the heat radiated by the light bulb, but it gives us a rough idea of the temperature progression. Now, when the lamp switches on, the temperature rises sharply. So we would expect the reflector to quickly expand, but there is solid contact. The lamp doesn't even flicker. Only after a while, when the temperature is increasing more and more slowly, the lamp goes off. Now the temperature drops sharply, but again, the contraction of the reflector doesn't seem to have an immediate effect on the light. How can this happen? At some point, I just so put the flashlight to my ear and listened to whatever sound it made. And I found another phenomenon. In fact, you can hear a tiny clicking sound right before the lamp goes on. Here is an amplified recording of that. What causes the clicking and what causes the on and off phases of the cycle being so long?
I could not find anything about the light bulb that could explain this, and I could not find a mechanical cause either. I guessed there must be something going on with the contacts, so I consulted literature on contact physics. Here is the resulting theory.
On a microscopic level, the contact surfaces are not smooth but rather like a landscape of peaks and valleys. Contact is only made at points where peaks touch. Also, the surface of the aluminum hull is covered by a layer of oxide and other contaminants. Whenever aluminum is exposed to air, a layer of oxide grows instantly on its surface. This layer protects the aluminum from further corrosion since it seals off the surface from the oxygen in the air. But it doesn't conduct electricity, so it must be broken before electric current can flow. This is achieved by a process which is called fritting. For this, the contacts need to be pressed against another until at some point on the surface the insulating layer cracks open. This creates a thin conducting channel through the layer. The channel is so thin that the current forced through it heats it up.
By the localized heat, a larger current is induced, causing yet more heat. This vicious cycle causes the contact area to melt, and the insulating layer gets destroyed within less than a millisecond.
At the end of the process, there is not only a good connection with low resistance, but since the metal was heated up and cooled down again, the contacts are softly welded together. They stick to another. Well, now the light is on and the reflector is expanding, so the pressure of the side contact on the aluminum hull reduces. This causes the pull on the welded contact point to increase until it breaks. As the contact point opens, less and less contact area carries the current. The last spot of contact heats up and melts. By this, a bridge of molten metal forms between the contacts. As the bridge gets longer and thinner, its electrical resistance increases. This decreases the current flow and the lamp dims down and the reflector stops expanding. What is now happening is basically the same that happens when the hot filament of a light bulb is exposed to air. It burns out. The contact bridge is so hot that it starts to vaporize. Because the contact bridge is not pure metal but contaminated with oxides and other material, there are spots in the bridge where relatively few conducting metal is present. These spots heat up even more, and the heat causes them to vaporize even faster. This vicious cycle gets even worse because the hot metal is exposed to air, so it is rapidly oxidizing. In the end, the hottest spot of the bridge explodes. This stops current flow, the reflector contracts and causes the switch to re-establish contact at the remains of the bridge. This happens quickly because the pressure is now concentrated on a small area. As the contact point melts, it may happen that the contacts are welded together again. But even if this happens, sooner or later the expansion of the reflector will break the welded point and the degradation of the contact point continues. Ultimately, the contact point either becomes so degraded that the contact cannot be remade quickly anymore, or the liquid bridge goes off with a final explosion. Now that the lamp is off, the reflector contracts and pressure on the contacts increases again. However, it will take some time to break the insulating layer again. That's why the lamp doesn't immediately go on again. Now, that has been the theory. Let's put it to the test with some more experiments. I thought it would be nice to see the contacts in action while they are doing the on-off cycling. Since you cannot see what's going on inside the flashlight, I took the inside out and prepared a bare bones flashlight that consisted only of the reflector, the light bulb, the switch cylinder and the tail cap with the spring. As a replacement for the aluminum hull contact, I didn't have anything suitable made of aluminum, so I took a new scissors blade made of stainless steel. Luckily, I could create a short cycle from this setup. Right before the light goes on, you can see a brief flash of light on the contact surface. After a while, the spot starts gleaming bright again at the same point where the first flash occurred. Then the lamp goes off. After a while, the lamp goes on again, but only for short. After that it stayed off.
As for the sparking, well, the initial spark can be seen only shortly, but it's very bright. That's the first contact spot overheating. Telling by the brightness, the heat must be enormous. The reason for that is that the inrush current is much higher than the current normally flowing because the light bulb is still cold and has a lower resistance. The light at the end of the cycle can be seen longer, and it's more shaky, just as the light of the lamp. That's the liquid contact bridge burning out.
Now, let's check if the contacts can actually weld together. For this, I tested the side contact on some aluminum foil under 3 volt. And it turned out that the contact and the foil were sticking together. But this only happened when current was flowing. After opening the circuit, the effect disappeared. This confirms the welding effect. But the welding comes at a price. In fact, the flashlight trick corrodes the side contact quite a lot. There are not only some small craters but also large chunks of metal missing on the surface. Well, we can now explain some observations.
As for the clicking sound, this is caused at the first point of contact. When the contacts close, the first point of contact overheats and rapidly expands or even explodes. This event sends a tiny shock wave through the flashlight that you can actually hear when putting the flashlight to your ear.
There are cycles with clear and stable on and off phases, particularly when the flashlight trick has just been started. But there are also cycles with a lot of flickering. The reason for that is the variable quality of the welded contact spots. If the weld is strong, then the on phase of the lamp is stable. Then when the weld breaks, the contact surfaces jump apart. This will at best generate a very thin molten contact bridge which quickly burns out. But if the weld is weak, then the contact surfaces start to separate slowly. This will generate a molten contact bridge that takes more time to burn out. As the bridge gets degraded, contact is repeatedly broken and re-established again. This may either cause the contacts to weld together again, or the contact point gets so degraded that the lamp goes off.
We can also explain now why the flashlight trick doesn't work when it's started without a certain heat-up time. In order to break the insulating layer, the contacts need to be pressed against another, which can only be achieved by contraction of the reflector. But if the reflector was only heated up a little, then it also has expanded just a little, and then it doesn't contract enough to break the insulating layer. And the other way around, if the reflector is hot enough, then we don't even have to create a loose contact. Just turn off the flashlight carefully. The gap between the contacts is now bigger, but the contraction of the reflector is likely strong enough to make contact.
Anyway, to summarize, the flashlight trick is caused by the reflector expanding and contracting, thereby breaking and making contact. The long and distinct on and off phases of the cycle are caused by complex events on the contact surfaces. First, when the lamp is off, some pressure is required to break the insulating layer of oxide and other debris that covers the contact surfaces. The lamp stays off until the reflector contracted far enough so that the spring in the tail cap inflicts enough pressure on the contacts to break the oxide layer. When the layer breaks, the contact area melts and spreads. The contacts get welded together. As the lamp goes on, the reflector starts expanding from the heat. It expands until it generated enough force to break the welded spot. Depending on the quality of the weld, the lamp either goes off quickly as the contact surfaces jump apart, or it goes off flickering as a bridge of molten metal is formed between the contacts which burns out. After the contacts started closing again, it takes some time to make contact. Because if the surfaces have jumped apart, then the resulting gap needs to be closed again. And if the last contact point burned out, then a new contact point needs to be created by breaking the insulating layer. Finally, as contact is made, the cycle starts again. Well, that's it. Thank you for watching.